Welcome to this presentation on trade-offs for parallel hybrid turboprops. My name is Michael and I work with Modelon. I'm presenting this on behalf of both Modelon and Modelon University. You can see the names of my co-authors on the slide. In the next 25 minutes, I will talk about turboprops and how to adapt them into parallel hybrids. I will talk about the methodology in terms of multi-point design and integrated modeling and simulation, as well as results of a conventional baseline and of various hybrids. And in the end, I will wrap up with future work and conclusions. Here we will discuss the parallel hybrid, which is also known as boosted turboprop. And you can see a schematic to the right. We have the familiar gas generator with the gas generator compressor, GGC, and the combustion chamber, CC, as well as the gas generator turbine, GGT, and also downstream a free power turbine, FPT. And this free power turbine drives the propeller via a reduction gear. We then assemble the parallel hybrid by attaching an electric drive to the free power turbine shaft, which is labeled 46 here. And optionally, we can also add an electric drive to the gas generator shaft labeled 4 here. And there are some benefits of this concept. It's still relatively simple to analyze and also install on the aircraft. Four variants of such parallel hybrids have been discussed and compared for turbofan cycles, and you can see the relevant conditions to the right in a single aisle mission. And we take inspiration from turbofan concepts of operations and select one of them for this work. And the first one in the list assumes that the aero engine must deliver a lot of thrust in takeoff and climb conditions, and then applies electrical boost in those conditions. And the power comes from batteries that are carried by the aircraft. And there is some hope that it becomes possible to downsize the thermodynamic core, what we call the gas generator in the previous slide, and then get some improvements for those turbofans. And for turbofans, that's the most widely discussed concept of operations. Second, one could also apply electric boost during cruise, and some people see benefits in this for turbofans, but there is also a lot of skepticism because of the weight of the required batteries. The third concept of operations shut down the gas turbine core during taxi and uses the electric drive to spin the fan for taxiing. And the fourth and last concept that we discuss here installs electric machines on all spools and uses them for transient control, in particular modulating the surge margin of the compressors during transients. And the one that we're analyzing here and applied to the turboprop is the first concept of operations that we've underlined because of its success for the turbofans. Let's talk about the methodology then that we've applied. This slide illustrates the classic single point design, and as most of you know, a single design point is used there to define the sizing of all components as you see it to the left, and then many off design points are simulated to yield different performance estimates on different flight conditions. Now, there are quite some limitations of this classic approach, and for that reason, we're using multi-point design. And here, design and operation rules on off-design points can also be used to define the sizing on the design point. And we therefore get this additional information flow from the right to the left. And we can define some of the design choices based on key off-design conditions. We use the Kyprianides and Kavalos scheme for the multi-point design of the turboprops. And yeah, to study an important part of the design space, we vary the overall pressure ratio of the turboprop, which you can see on the upper right of the table. And this is a key cycle parameter for the thermal efficiency. And of course, this scheme also prescribes power instead of thrust, as it's customary for turboprops, because that's really the main output of the gas turbine, which is designed separately from the propeller. And whenever we're looking at hybrids, we prescribe the free power turbine boost power explicitly, as it is done in most cases in the literature for the turbofans. You can see this at the very bottom of the table. And to the lower right, you can see a reference, the last one, if you are interested in an overview of these closure equations for the hybrids and learning about one alternative approach to define the design of parallel hybrids, please take a look at that. Here is some information on the gas turbine and aero engine model implementations. All the models were built in Modelon Impact, the cloud-based system simulation platform. And to the left, you can see some literature references to the underlying performance and weight estimation methodology. To the right, you can see a typical model diagram. It contains the gas generator components and the free power turbine. There are also two gear stages and the electric machine at some intermediate shaft speed. And to the lower left of the schematic, we can see a utility block through which the typical flow station notation is defined, in which we're also computing overall quantities. When building multi-point design models, the turboprop model built out of the individual components that we just saw on the previous slide can be instantiated several times. And of course, that is done once for a design point and several times for off design points. You can see them on the slide here. And then engine model instances are connected to each other through utility models that contain the typical design and operation rules. Thanks to the standardized Modelica modeling language, all graphical and textual representations of the models are consistent. We can also always open up the code editor and change the automatically created code by hand. To yield an integrated simulation and design, we must also include the physical models of the electric power system, and these can be introduced just as other variants that one might want to study with such a placeholder here as shown for the electrical system. And then that placeholder can either contain just the electric machine or the whole electric power generation and distribution system covering the machine, cables, inverters, batteries, and so on. Here, we're showing a few details on the geometric dimensions and definitions used in the electric machine design. And this is a permanent magnet synchronous machine, and we assume a constant cooling flow rate of 3 kilograms per second of cooling oil for all cases. And you can find some references describing the analytic sizing procedure in some more detail. All the computations were run also on Modelon Impact. This is a system simulation platform which offers you multiple views and means to access modeling and simulation. To the left, you see the graphical desktop with drag and drop, custom functions or microscripts to automate workflows interactively. In the middle, you see the notebook interface for sophisticated analyses. And to the right, you see web apps and browser-based dashboards providing more casual interfaces to sophisticated simulation. And in this work, we've used the two views shown to the left and the middle. With these views, we can then create a customizable workflow covering all the required steps. We can start with using drag and drop to create the model of the single point turboprop. We can then save and name the simulation results of that single point model in the user interface. And we can also use these custom functions to automatically generate a stub of the multi-point model. We can then extend it with all the design and operation rules that we mentioned before. And we can converge it using the guesses of the saved and named single point simulation results. So then we have this converged multi-point model. And all of this is done with these microscripts, or we call them custom functions in the user interface that you can evolve, adapt, read, and use from the user interface. And lastly, we can then use that multi-point model, which has been converged interactively on the first simulation run, for a range of batch analyses. So for instance, in the notebooks, run all the studies that we've then used to assemble the simulation results that we're about to show, or exposing those trends through web apps. So let's move on to the results. Here are some cycle performance results showing the power-specific fuel consumption over the overall pressure ratio for a conventional baseline. We're using color coding of the plots. So one color typically corresponds to one case, independently of what subfigure you're looking at. For instance, orange will be rolling takeoff conditions, and green will be cruise. And we're showing here different variants of these plots of fuel consumption over overall pressure ratio. And from left to right, we're increasing the T4 temperature, so turbine inlet temperature. That means that the cycle temperature is getting higher if you move from left to right. And here we see that the optimal overall pressure ratio initially increases from 15 that we see on the middle row to the left to 16 for that intermediate T4 temperature of 1325 Kelvin, and then starts reducing again. You see the green arrow highlighting the minimal cruise SFC value. And again, as we increase the cycle temperature beyond that threshold, the optimal efficiency OPER is reducing again. Additionally, from top to bottom, we see a variation in the turbine blade cooling. This also influences the optimal overall pressure value for lowest cruise-specific fuel consumption. And if you go from the bottom to the top, you apply less cooling, so you allow the blades of the turbines, both the gas generator turbine and the free power turbine, to become hotter. And if we look at less cooling, the top image, the 1250 Kelvin uniform blade temperature, we get the lowest SFC at around 16.5 OPER. If we have more cooling, if you look at the bottom, the 1115 Kelvin, we get the lowest specific fuel consumption at OPER 15.5. So that exposes some of the traits that you're seeing on the conventional baseline. What about mass estimates? We're showing them here again as a function of the overall pressure ratio with the same variation of the cycle temperature from left to right, moving to a hotter cycle, and from bottom to top, moving from more cooling in cooler blades to less cooling in hotter blades. First of all, we see now color-coded different components, the different gas generator turbo machinery components, the free power turbine, and also the total mass, for instance, that's the black line. And they contain discontinuities. They always occur when the required number of stages in the turbo machinery changes. And we see the corresponding masses for the overall pressure ratio values that we've highlighted as leading to optimal SFC values here. And we can, of course, work with those, or we can look for alternative designs with slightly lower mass. This is typically due to the green line, so the mass of the free power turbine at slightly lower overall pressure ratio. You can still get away with a lower stage count on the free power turbine. So those are highlighted here with the gray arrow. And they typically use overall pressure ratio in the range of 13 to 15 for the parameters that we considered in this study. Lastly, still on the conventional baseline, to illustrate some of the model fidelity, we're showing some flow paths of the fully axial turboprop here. And if we go from left to right, we show 3 different designs with different overall pressure ratio values. We can see how the last stage gas generator compressor blades become shorter and shorter as we move to higher overall pressure ratio, and also based on the pull stress for the discs and the shaft speeds, the optimal disc type can change. And on the far right, for overall pressure ratio 16, we see the 3-stage free power turbine. And this design with overall pressure ratio 16 is also the one that we've hybridized in the following. We first analyzed single speed designs. You're possibly familiar with that due to certification requirements, some turboprops can only run at a single shaft speed independently of the rating. So we're looking at these here. And to the left, we see some results for a conventional baseline. And the paper describes the overspeed capacity requirements that result from that. They're actually quite challenging. And you can see at the lower left of the slide where the overspeed requirements apply between the free power turbine on one hand, or the gas generator compressor and gas generator turbine on the other. And as a compromise, we're suggesting here this intermediate single speed design at 28 to 100 RPM, which reduces the overspeed capacity requirements and yields a 6% penalty in the specific fuel consumption over the variable speed conventional baseline. So you see the 0.246 kilogram per kilowatt an hour specific fuel consumption result being highlighted there. And to the right, we see some results for a parallel hybrid, and we see a mild benefit of the hybridization here of 0.5% in the specific fuel consumption in comparison to the single-speed conventional design. And yeah, as a side note, the gas generator compressor and gas generator turbine over speed capacity requirement disappears for the parallel hybrid. You can find more details on those in the paper. We then looked at variable speed hybrid designs, and here we were not varying the overall pressure ratio, but we have selected the best specific fuel consumption baseline and hybridized that with a range of power values. And the results that we show here, they apply 250 kilowatts of boost power during takeoff and climb. And for that design, we wanted to study the impact of varying gear ratios per stage while maintaining a consistent 1 to 15 total gear ratio. So we see a range of first stage gear ratios here, ranging from 1 to 5 on the left. So a slowly running electric machine at 1 to 2 on the right. So an extremely fast running electric machine. And we also see the size of the electric machines now in the flow path. As expected, it gets lighter and lighter as we design it for higher shaft speed at the same power output. Here are the mass estimate results. As expected, the total mass is reducing if we run the electric machine faster. As described, the turbo machinery is not altered, so there is no change to other component masses than the electric machine, shown in purple here. But nonetheless, the parallel hybrid is always heavier than the conventional turboprop. And here we're only looking at the mass estimates for the electric machine, which already yields a 20% plus increase of the powertrain mass. Now we were getting this mass increment, but also an complexity increment, and they will only buy their way onto an aircraft if they brought substantial double-digit fuel burn improvements. However, we're not seeing any relevant benefit of the hybridization with respect to fuel burn for the variable speed designs. Therefore, the parallel hybrid is barely attractive for these variable speed turboprop designs. For completeness, the paper describes how the model of the electric machine has less accuracy for extremely high machine speeds that we show to the right of the plot here, because it only solves the fundamental harmonics. Taking higher order effects into account, it would be expected that the benefits of increasing the shaft speed vanish at some point. To summarize, the work provides insights into the cycle design and speed selection of both conventional and hybrid turboprops. It is shown that the selected concept of operations does not yield benefits for a parallel hybrid turboprop. And the reason is that the typical rating structure does not impose contradicting requirements, as we've seen for turbofans, and therefore the fuel burn benefit is comparatively low in contrast to the pretty big deterioration of the mass of the powertrain. In the future, it would be relevant to analyze other concepts of operations, such as the transient control for the turboprop, and optionally to take higher order harmonics into account, which, however, will hardly be possible with pure system simulation, but requires field simulation, however, such as 3D finite elements. With this, I'd like to thank you for your attention, and I hope that the material presented was interesting for you. Please join us for the live discussion or reach out via email.